In this topic, we're going to be looking at things that are oscillating. The main focus is going to be the mass spring system and the simple pendulum, but you can see some other examples here, like a buoy floating in water, atoms in a molecule, or even current in a circuit. We need some common terms to describe oscillating objects. So firstly, we've got the equilibrium. This is defined as a point where the displacement is zero, or this is where also the point where the resultant force is zero, and this is where the object would come to rest if there was no disturbance in the system. Then we've got the displacement itself. So displacement is measured from the equilibrium. It can be positive or negative. So it's the distance and direction from the equilibrium because it's a vector. And normally we're going to represent that using the letter x. Okay, then we've got the maximum displacement from the equilibrium, and that's amplitude, and that's given the capital letter A. Okay, so the capital letter A just represents amplitude, and with the simple pendulum, we can't mistake the amplitude of the displacement from the equilibrium and the length of the pendulum itself. Okay, that's a common term that students get mixed up. Those are two different things. Okay, next we have time period. There's a time taken for one complete oscillation. So in the case of the mass spring system, we'll time how long it takes to go from the equilibrium to the maximum and then to the minimum and then back to the equilibrium. So that's one complete cycle because it has to be in the same displacement and going in the same direction as well to be considered one complete cycle. Of course, you time multiple oscillations and then you divide it by the number of oscillations to find the actual time period. For the pendulum, we can do something similar and time how long it takes to go to the same point in the same direction again. And then you can use a time period, which is given the letter capital T, to find the frequency, which is f, and the frequency is the number of oscillations per unit time, and they're related through this equation. As you can see, a lot of the terms here is an overlap with the circular motion topic and the waves topic, is periodic motion. Here we have a pendulum that's going to be swinging. We've got another one which has got the exact same length, but a red one here. The question here is a time period of two identical pendulums of 5 seconds. The red pendulum is 2 seconds ahead of the blue pendulum. Calculate the phase difference between the two pendulums. Okay, so phase difference is the exact same definition as in waves topic. The phase difference is a fraction of a whole cycle. One point is ahead of another point measured out of 2 pi or 360 degrees. Okay, so 2 pi represents in this case one complete oscillation. Okay, or 360. Okay, so we can use the same equation here, the time difference divided by a whole time period. Okay, the time period of one oscillation. So in this case, 2 seconds ahead out of a 5 seconds for a complete cycle. That gives us 4 pi over 5 radians or 144 degrees out of it. Okay, the time period of a pendulum is 5 seconds. Calculate the angular speed of the pendulum. You might be familiar with the definition of angular speed from the circular motion topic, which is change in angular displacement per unit time. In this case, it's actually not the same. It's got nothing to do with this angle over here and how quickly that's changing. Instead, it actually represents the rate at which the phase of the pendulum changes. So you can use the same equation here, 2 pi divided by the time period. So in this case, 5 seconds. So that gives us how quickly the radians is changing per unit time.